And welcome everyone to this webinar hosted by Jacinto Barese and myself. Jacinto is my co-chair of the Technical Committee of Human Factors in Robotics of the IEA, and we are very happy to host this webinar, this first webinar together, and we are especially very happy about the three distinguished speakers we could win to present today. And just to give you an idea what the technical committee is about, right? I mean, basically, what we want to achieve is to bring together people from all over the world who, in some form, research or work with robots, and of course, who have the human, a special interest in the human and the human user and how people interact with robots in all kinds of different areas. But today we want to focus on industrial human-robot interaction. And we would like to encourage some discussion. We would like to encourage exchange, but also would like to encourage to network with us, with the speakers. So, and if you're interested in joining the technical committee, just write us an email and then we can collaborate from that on. Today we have three speakers. So we're going to start with Jackie. He's a professor at the Robotics Institute at the University of Technology in Sydney, Sydney, Australia. Then we have Wanzu Kim. He's an associate professor at the Hanyang University in South Korea. And then we have Gianmarco. He's a technical fellow at the University of Sheffield in the UK. And I'm really excited and looking forward to all of your three talks. After the presentations, we will have some time to discuss, to go deeper into the presentations, also to take some questions from the audience. So please be ready to discuss and engage with the speakers. So Jackie, which by accident is under my name currently, but this doesn't matter. So I give the floor to you, and I'm looking forward to your presentation. Thank you.
You're still muted.
Yeah, sorry. Thank you very much, Patricia. And this is my great pleasure to talk about our research on human-robot collaboration with physical contact. And the talk today will be more focused on human models for PHRC. In industry applications, and we can see still many tasks human workers are still doing, like this, what you can see here is very physical intensive tasks in construction. And in manufacturing as well, you can see human workers are still doing a lot of physical intensive tasks. In healthcare as well, moving patients from bed to wheelchair or to other places is very labor-intensive task as well. So how can we really help human workers to do this kind of tasks? One option is to develop autonomous robots, and the robots can really do the tasks without human workers involved. So that may not be a good option in many industry applications because humans' environment is very critical, particularly in the healthcare and the aged care industry. So what we think, we should have robots working together with the human workers to do the task jointly. This is what we think will be the better option. So then in order to do that, here's one example. For example, if we have the robot arm or industrial robot here, and the human workers hold the handlebar, and we like the robot to understand what this human worker wants to do. And more importantly, the robot should work out how much support the robot should provide to the human worker. So for different human workers, the support should be different. And particularly for some workers, if they have the muscle fatigue, then the support should change. So if we want to have a robot which is intelligent enough to understand the human worker and then work out the support as needed, then we have many questions to answer here. The first one could be, for example, what kind of support the robot should provide to the robot, to the human. Second is really the safety issue. Third one is about the control. So there are many other questions as well. So the main purpose here is really try to combine the strengths of humans with the strengths of robots. So, and what is the best way to combine the strengths? We have been doing this research from different to address different topics here. For example, perception, how robot is going to perceive the human operation, and also human models. So what kind of human models we should have in order to enable the robot to understand human workers and then to provide support to human workers. Of course, brain-robot interface, trust modeling, dynamics of human-robot collaboration, and human factors and ergonomics as well, safety and control. So here I'd like to talk about some of our research here. The first one is about the pose estimation. We talk about upper body pose. In live environment, the pose estimation could be easy because you can have many sensors, right, installed in the environment. But in very industrial application, particularly in the field environment, this is very challenging to do. To have robot, to have many sensors placed there. So we like to have very few sensors there, which we can really provide the information we want. This is one challenge. Second challenge is that, for example, in manufacturing or in other environment, it could be very dusty. And in this very dusty environment, how can we really perceive the pose or estimate the pose of the human body? So this is very significant challenge. What you can say here is about a human worker doing blasting, could be used gauntlet or could be used steel grid. So the dusty could be different. Then how can we really get the pose? So we came up with a way to solve the redundancy of the upper body or the upper limbs. So we assume that we know the hand position, and then we can measure the torso position. Then based on the torso position and the hand position, although the elbows and the shoulders still have many freedoms, they're still redundant, but we can work out the way really to find the pose which is reasonably accurate. So by using the kinematic model of the human body. So this is one of the research works we did. Then based on the pose of the upper body, we like to estimate the strength of the hand. So in order to know the strength, we can do many things, but one way we did is really try to use the biomechanics model to really estimate the strength of the upper limb or the limb, the strength on the hand. And based on the strength on the hand, then we can really work out the support. The strength changes based on the, if the pose change, the strength change. And also if the muscle get injury or get fatigue, then the strength changes as well. So how can we really get a reasonable estimate of human strength in various pose and also in various muscle conditions? So biomechanics model can give us some information, but may not be that accurate. So that is one of the challenges we have been having, and also we have not addressed there in terms of the accuracy or of the biomechanics model of the upper limb. Another model we looked at is about the hand model. And for example, you can see how the human hand is going to hold a handlebar. the different way to hold it then tells a lot of information about whether the human is really engaged or whether the human worker is doing something different or not in the right way. So we use the sensor ways, and we use the model of the hand, then work out the way using machine learning algorithms to identify the way a human worker is holding the a handlebar. So this information we found is very, very useful. Another model we will look at is really about the trust model. The trust could be robot to human trust or human to robot trust. So we think this is important, particularly when human and robot working together. If you look at the in the upper right corner of the video, then you can look at this. There are many ways to build the trust model, or one way is really performance-based. For example, we can use the safety performance, singularity performance with the industry robot arm, smoothness, physical performance, and the cognitive performance. So based on this performance model, then we can build the trust. And this trust depends on the performance of the human workers. The robot can use this information to judge whether the human worker is really engaged or is really focused on the task. Of course, we can look at another way, human to robot trust. So we can use machine learning and the really to come up with the reward function and the decision-making policy, and by optimizing the parameters, then allow the robot really to learn the parameters, or the model to learn parameters, and then to predict or to predict the trust. So this is another way we can do, or we have tried.
Estimation of human trust.
Probably I just like to, due to the time issue, probably I skip this video. Human preferences in terms of how, particularly when humans and the robots, industry robot working together, singularity is another issue. Because when human worker is really moving the robot arm to do a real task, then they do not pay enough attention to the singularity of the robot. So how can we really handle the singularity? So we came up with a couple of ways to address this. But one of the things we found is very important is about the human preferences in using damping to manage singularity. So we did human subject interview and the experiment, and we found that human really like to have the quick response, and they really to try to avoid or to reduce or to mitigate some issues there. Physiological signals can be used really in physical human-robot collaboration. Many people have been doing this. What we have been doing is really use the EEG signal and to predict the performance of the robot. If the robot is not doing or is not doing what the human worker is expected, then we can find the cognitive conflict. And this information can be used to adjust the robot control. And then this is what we call the neuroadaptive framework we developed. And what we found this way, the performance is really improved. The cognitive conflict is really reduced by incorporating the information to incorporate the cognitive conflict information in the control of the robot. How mental workload affects physical performance. This is another thing we looked at as well. For example, what you can see in the video, we suggested the human worker to move the cursor by moving the robot from the center to the to other point. And at the same time, we suggested the human worker to do a calculation. Could be very simple, 1 + 1, or could it be more complicated? And the complexity of the calculation indicates the mental workload. So with this, with 24 participants, and what we found here is the physical performance really is affected with the increase of mental workload. Another thing we looked at is really about the cognitive workload or mental workload, how this workload affects the error awareness of a human user in physical human-robot collaboration in real industry application. So what we found, this is important because when humans and the robots working together for many hours in a day, and there could be errors, and the error could come from the robot, or for example, collision with the environment, or could come from the human worker. So then we did experiment with 24 participants as well, and we assumed some unexpected stopping of the robot. And then we really found that the mental workload or cognitive workload really affects the level of awareness of errors. So this what we found is very helpful as well, particularly for the physical human-robot collaboration. Human models can be really used for control. Here is one example. We use the human model, the operating biomechanics model, to use this model for calculation of the support a robot should provide to a human worker. So you can see here we can have the task model that basically tells us the strength required from the human. And also we have the strength model that is based on the strength. Then we can work out the assistance, for example, in terms of percentage or or a absolute value. Then based on this, there is a guide here. And this guide is what the robot should provide to the human. So, and we tested this in our system and it worked well. Other thing is really about role change. When humans and the robot working together, we should have the role change. So if the human is not doing the right thing or is making mistake, then the robot should take over or the robot should take some action. Here is a very simple example experiment we did. So the human worker is supposed to move the cursor in the area between the two red lines. But if it is moving outside, then the robot will figure out, the worker is not really focused on this, and then the robot will take control. And who is in control is what we call the role change. Human models can be used for safety as well. This we think is quite important. For example, safety by assistant paradigm based on human models we mentioned before, or safety by interaction design. And of course, we have other measures for safety for human-robot collaboration as well. So we applied our research in developing real robot systems that can be used by people in manufacturing environment. So this is the first robot we developed and tested in a real company to do the blasting of components. You can say this is the worker who never used the robot, and they use this robot to for cleaning the surfaces of steel structure. So the feedback was very positive. So second application we did is really applying the research for human-robot collaborative installation of screws on the construction site. And you can see from the left video, the video in the left, and you can see it's very challenging for human workers to consistently install long screws to fix timber board. So, but if we work together with the robot and the human worker just indicated to the robot where this screw should be installed, then the robot is going to do the job. And we found this is very helpful. And this robot has been tested in the real construction site. And the feedback from the company was very, very positive. For healthcare and aged care, and we implemented the research outcomes into a smart hoist or robotic hoist. And then nurses can easily use the hoist to move patient, and the feedback from them were quite positive as well. So probably due to time constraint, probably I'm going to stop here instead of talk about other applications we've been doing here. And again, so many research topics we've been trying to do, and we just only touched some of them, and even for the topics we have been doing, still have a lot of things we like to do. So this could be the opportunities for us to work together in the future. Okay, I'd like to acknowledge many people who worked on this project, and thank you very much.
Thank you very much, Diakay. That was already, I think, really, really interesting. And I can already see that there are some questions popping in. And I also have myself many questions. But I would say we will let all the presenters speak first. And then maybe I try to, maybe we can cluster a little bit the questions and tackle them towards the end, if that's okay with you. And now I would like to hand over to Wanzu, who is going to speak about Industry 5.0 and human-robot interaction. And I'm looking forward to that talk as well. Very much. The stage is yours, Wanzu.
Okay, thank you for the introduction. And then could you see my screen perfectly? Can you see my screen?
Yes.
Yes, we can, yeah.
Okay, so let me start here. Okay, thank you for having me here this webinar, and then let me introduce myself. My name is Wansu Kim, and an associate professor in the Hanyang University in Korea. So today I would like to talk about the human-robot coexistence and then share the dynamics for the Industry 5.0. So as we already may know that, and then we heard about many stories about this world population thing issues. So global demographic shift is working like this way. So almost in the 2018s, actually the people above the 65 years old age is outbounded of the younger people, and then we expect it like it's in the future, like a 2050 or the 2100 is getting and over the like his age, the society and population is getting aged for sure. So to regard this kind of issue, actually, like I said, the robots we expected is one of the some solution for our future. So some people say that yeah, maybe the robot automation is one of the solution, like as in the manufacturing, healthcare, caregiving, logistics service, and construction or agriculture things. Everything we can made it like as some fully robot automation could be the one of the solution for that things. But the truth is that actually many people is expecting such kind of the fully automation, but somehow actually we saw some failure cases already, like it's some limitation of the fully automations. So the Elon Musk actually is already tried it to make the fully automation in the sense for their manufacturing the line for the Tesla. But he mentioned that like is that they're making the fully automation construct and the line for the Tesla they're making. But he mentioned in the Twitter, now is X, say yes, it's a flexible automation and Tesla was the mistake. To be precise, my mistake. Human are underrated. So why this is kind of happen? Because as we know that actually these days also like as a humanoid robot and the many robots is introduced, but actually it was not really successfully to integrate it into this the manufacturing the environment, because we are missing some part like as a human. So to do this way, actually the people was thinking about it this kind of the issue. So people was thinking about what is the we are missing, what we are missing from the industry. Or so probably we have heard about many stories about the industry 4.0. Of course, I mean the industry 4.0 is successfully introduced, and then they're going to integrate many technologies into the industry, but still we are missing something for that things, like as a human and the resilient, sustainable. So in these days, there's a start from Europe, but there is a start, the new way, new era is called it Industry 5.0. It could be more added some topics like as a human-centric, sustainable, and resilient. So unlike the industry 4.0, the industry 5.0 is a more like is combined with the humans, and then how do they collaborate with them, like such kind of things. So my research topic actually is more concentrated on the human-centric aspect. So in this way, so industry is dedicated to serving the people, not shifted from the technology. It's centered to the human-centered approach, and then the provision of the safety and high-quality job, and then the workers as an investment, not adjust the cost for the things. So to do this, I was thinking to what kind of the technology we needed and what kind of aspect we needed is this, there can be distinguished as three categories, like is improvement and the enhancement of the labor forces, and then prevention of the losses, and then assistance in the labor forces, and then restoration and then functional recovery of the labor forces. So to do this, my research topic can be distinguished in the three categories, like as ergonomic and safety, and then shared autonomy and interfaces, and also exoskeleton robots. But today I would like to more focus on the ergonomic and shared autonomy, and then here I can just briefly show that what kind of exoskeleton I have been working for that, and then this kind of low body exoskeleton to carrying some heavy load or some new type of the mechanism or actuator is developed for make some more efficient behavior, more improve the productivity. But today I just more focus on the ergonomics and shared autonomy things. So probably the ergonomics is quite familiar keyword terms in this society, and then ergonomics is like we're gonna trying to monitoring what kind of factors can be affected the human risk, the risk factor for that. Like when the people or workers have some repetitive task or the heavy manufacturing task, there's some possibility to having some occupational injury or chronic pain. So to mitigate such kind of things, many ergonomics way is to monitor and then they analyze their posture and then some working environments. So and then they can provide us the guidance to avoid such kind of the joint overloading or there's some risk factors. But in this way, actually, there's some more, the classical way is we can say that it's a pen and paper method, and then it's this kind of the ergonomic approaches happen when there's some the chronic pain or occupational injuries is already exploded into the human body or the working environment. So my idea is that what if we can integrate such kind of thing to the human level collaboration aspect, and then the more the acting on the real time aspect, like is developing the human level collaboration technology to encourage and guide the human co-workers to perform the task in the ergonomic way as possible in the real time. So to do this, we have to more focus on how to be monitor the humans, the road variation in the real time. And then second is how could we provide some feedback to the users to mitigate or to avoid such kind of the risk factor. Indeed, and then we're just thinking how could we control the robot? What if we can control the robot partner to assist the humans to mitigate and to avoid such kind of the risk factors in the same time? So first approach was that we are trying to investigate what kind of the risk factor we can have considering in the real time, like as a joint displacement, joint velocity, joint acceleration could be some kinematic the information can be considered during the task, but also like the dynamic aspects such as the offloading joint torque, what we have developed during this work, though how much the load could be affected on each joint, and we're gonna trying to make it monitor and then to anticipate the estimated some load effect and the risk effect in the real time. And then also the related to this in the joint fatigue can be estimated, some powers and the changes of the powers or compressive forces everything can be detected, everything can be measured and then they estimated through the real time through the human kinematics model. So we made this kind of aspect in the open source data set, and then we have analyzed the many different type of the task we haven't considered. And then afterward, since we have know about what kind of risk factor can be monitored in the real time, and then the second approach is that what if we can provide some feedback to the users in the real time to avoid such kind of risk way? So here my colleague the Marta is from IIT. So she was holding some kind of the heavy object on their arm. So in here, as you can see, so as soon as when the load is detected, and then the human kinematic model is built up on this way. And then also you can see some different colors, like is a green, orange, red. That means that indicate the risk of in terms of the ergonomic way. So here, when you just align on the back, somehow the risk factor is getting increased. So the overloading joint is getting increased. So all the indicators shows the lead, but if the load is come close to your COM position, all the indicators shows the blue. That means that actually it's more safer. But somehow in the working environment, actually, it's not easy to see those kind of the screen all the time. So the other idea is that we can make those kind of the devices can be wear on the body segments directly. So the idea was the same. So we can divide the 3 different level of the vibration can be provided through these ergotech devices. Then when you're wearing this kind of the devices, as soon as when you're moving along the task like is lifting or the carrying something, these ergotech devices can provide some vibrational feedback to the users. So the users can easily understand, okay, so this posture maybe is not really safer, so I can adjust some posture to minimize this vibrational effect. So indeed, this kind of work can be integrated into the robotics application. So here we have been performed during the KUKA Innovation Award in 2018. So the KUKA robot has the holding some of the pieces, and then the human subject was me. They're holding some heavy tools, like it's almost a 2.5 kilograms of the load in the machine tools there. And then I'm just ready to holding this kind of tool for performing some kind of the task. But robots, so trying to bring those kind of the pieces in front of me, but as soon as the robot is recognized, okay, so this posture maybe not really ergonomically good posture for that. So the robot is trying to adjust it to make sure that the ergonomical posture as possible. So even when I just moving around, there's some different, the hand, they use the tool and then change the position. The robot is trying to adapt the behavior to provide a more ergonomical posture as possible. On the right side also is a similar approach that we have, but it's more related to some fatigue effect as well. So here the left one is holding some heavy tools, but what if we can holding just lightweight tool? So but still in this way, still we have some possibility to have more the ergonomic damages can be affected during the like it's a long time the task. So here the fatigue is also can be like is accumulate. We just anticipated the fatigue effect, which is accumulated to each joint. So as soon as the time is past it, some fatigue is getting accumulated, and then the robot is trying to adapt their behavior to mitigate such kind of the fatigue effect. So for the long horizon task, maybe this kind of the approach could provide a more intelligent, more advanced technology to collaborate with the human in the more safe way as much as possible. So we're keeping working on this kind of direction. So based on the human model, like we're trying to make the human model, simplify the human model as much we can, and then the human is we're trying to anticipate what kind of the effect to provide the risk provided to the humans, and then we have anticipated what kind of the ergonomic state the protection can be founded, and then how could we generate the motion, but not unlike the previous the step, like at this time actually we are trying to provide the whole trajectory during the task, which means that we can try to keep the more ergonomic path as long as we can collaborate with the humanoid robot or the mobile manipulator or the other kind of the robot things. So here we can show that how could we guarantee that such kind of the ergonomic aspect through and then in the meantime they can also provide some more efficient working the task and target it. So here is you can see that the ergonomic aspect can be reduced. In our proposed method can be kept the more the less the risk in terms of the ergonomics, and then keeping them a higher the work efficiency as much as we can. So this kind of behavior, of course, is not only just for the human robot interaction and then this more human monitoring system, but also it has to be guaranteed that how much the robot can be provided the safer behavior to the users, so not to like as some offended the humans behavior. So in here we have been working for that how much safer action we can guarantee that during the human level collaboration, like as in some during the impedance control or the admittance control approach. So here we just propose that the energy tank based method. So this energy tank based method is guaranteed that there's some fixed energy we can use during the task. So in this way, actually, even when we move around to the user, to the robot, and there was sometimes we touch this, sometimes we hit it, and the robot is just trying to push me or the pulling me. In that sense, still we're trying to guarantee that all the behaviors are safer for during the interaction task. So as much as we so that show that during this kind of the disturbance is affected to the robots, still we can guarantee that all the safety due to this the fixed energy tank approach, even though when the human is pushing the other joint, still we can guarantee that things. And the similar approach also can be affected to the exploit with the control diaphanous function and the model predictive control. So we can try to guarantee that the safety also in the meantime, we can try to adjust the impedance variable for safety and then guarantee that there's a more efficient action during the task. So like as when you're trying to touching or the leaving we're missing some context in the meantime, still it can be guaranteed that all the safety behavior as much as we can. So this kind of the robot's behavior, of course, we can extend it with the mobile collaborative robots. So like with the mobile collaborative robot can be shown like as combined with the more the ergonomical way, and then like as working like as exoskeleton. Or we can combine with the human level collaboration behavior distinguished with the other the task reliable things. So how much time we have? Actually I cannot see that the time. This
is why I raised my hand. So if you would
okay.
get to the end with
Okay, yeah, I was just trying to go to the end. So yeah, so here I would like to show more I would like to give more detail, but unfortunately I don't have that much in the time for that. But one last thing I would like to show that, so like as an interface wise. So of course, I mean, the human level interaction with working with the robot is more important with how to control the robot and how to model the humans in somehow. But also the thing is that what kind of interface we can consider during the human level collaboration task. So here I recently developed the new open source the functions. Actually, this is really cool that I wanted to show that. So it's called that the ROS MCP. Actually, someone have interest in it to collaborate LLM somehow to control the robot. So because you're not really professional on the robot control, maybe you is limited to use such kind of the robot behavior to working with the LLM or something. So in this way, actually, the new MCP server can provide that kind of a function. So if you're not have any knowledge about some robots, actually, rather than trying to analyze all the function of the robot, then we can just simply control the robot through like this. So LLM can understand what kind of robot function it has, and then how to be controlled it. And then we can just say that go to the other side. It's just simple command can be provided, but the robot can act like this way. So this is the end of my the talk, and then so my research trajectory is our work shows that the clear path from the reactive assistant to the proactive partnership. So my future goal is the long term and then co-adaptation is creating a synergistic partnership that enhance not just the physical independence but well-being and the quality of the life for the aging in place. So thank you for having this. Thank you for watching the seminar talk. Thank you.
Thank you so much, Vanzu. This was also, I think, very, very interesting. And I think it's always really a pleasure to get an insight into your research. And I can already see that there are a lot of questions popping in, and I would like to encourage the audience, please do so. Maybe you could just indicate to whom the question is directed, if it's to everyone or to one specific speaker, and then we will try to answer as many questions towards the end. But now I would like to hand over to Gianmarco, and I'm also really curious about your research. The stage is yours.
Thank you. I'm assuming you can see my screen already. Yeah,
Yes.
perfect. Cool. So my presentation is going to be about human-robot interaction industry, about sort of the MRC approach, and I'm going to talk in a second what the MRC is. But just want to sort of preemptively say that we are a bit less academic and we're more sort of closer to the industry side. So we're going to be less academic and more sort of see what industry does at the moment, which is not as much as we would like to see actually. So just a brief introduction about myself. I don't tend to be this sort of self-centered, but this is an adapted presentation that I gave as a guest lecturer at the University of Sheffield. So they were asking me about sort of who am I and what brought me into robotics. So yeah, I'm a technical fellow in robotics research at the MRC. That stands for the Advanced Manufacturing Research Centre. And that's sort of one of the flagship centre of research at the University of Sheffield, where we sort of cover a lot of research in advanced manufacturing, and I'm going to talk about that in a second. But I'm also the co-theme lead in manufacturing at Sheffield Robotics, which is the networks of universities in Sheffield, both University of Sheffield and Hallam, and I sort of try and stir I'm the lead for manufacturing and try to stir the research that happens at both universities in manufacturing, so it's more appropriate for what industry in manufacturing specifically needs. And then finally, I'm together with Jacinto, who's here again today. I'm on the executive board for the UK RAS network on the internationalization pillar. So very quickly, so where the MRC works is, so I'm assuming people know what the TRL levels are, so technology readiness level. We tend to work around 3 to 7. So we tend to sort of attack in a way what's called the valley of death. That's usually where research dies. That's where we've got sort of PhD research. They go to a very mature level, they stop at TRL 3, and then the research dies there. So what we try and do is we collaborate closely with academia. We try and see how can we sort of push this research towards the higher TRL level, and in a way that sort of industry can then take it up and then move it towards commercialization. In terms of areas, the AMRC covers quite a lot of sort of topics of a specific technicals area, and we sort of the main 3 pillars are sustainability, digitalization, and productivity. So if any industry has sort of a system or a production line, we try to make it to innovate and make it sort of better and faster. But in terms of technical areas, we do high-value design and rapid prototyping, component manufacture, both composite additive but also casting, subtractive processes, automated assembly, smart factory inspection, and through-life engineering services. And I have to say, we've got a few centres across the UK, one in Sheffield with different buildings on different sort of areas, and then we've got one in Wales and another one in Northwest, still in the UK. So again, I was asked this question when I was giving this lecture at the university. So what's my goal? Why I sort of started this sort of journey in robotics, why I work in robotics. And my answer is that I want to see sort of a world where robots are omnipresent. I want to see robots everywhere in sort of in everyday life. But then obviously that's not the case. Some of those pictures were generated by AI, and then you can see that we don't see robots in our homes helping elderly people. We don't see robots sort of collaborating with us in our homes, sort of like talking to us, or even like in public spaces. And so what do we need to sort of get to that point? So I believe that there are sort of 4 different areas that we need to sort of improve. First one is democratized programming, and I'm going to try and cover at least the first three. Simpler and more intuitive robots that can adapt to us comfortably, and then robots that can understand and respond to human needs, including emotions. And that's sort of the long-term goal. I don't think we're going to be seeing that anytime soon. And that sort of translates to what's called the theory of mind, which, if we've got time, I'm going to touch on later on. But then, as you can see, these are not necessarily things that apply directly to manufacturing. So you might be asking, if this is my goal, why did I go into the manufacturing sort of sector? And well, that's because in theory, it's simpler, or at least compared to everyday human life. Because in manufacturing, we've got environments that are more structured. And so the goals, there's not this need of general purpose robotics that we're all trying to achieve. Because the system is so specific that you can sort of adapt the robot to the environment around you. So if you can solve those problems, we can see them solved within years, really, not just in my lifetime, because potentially we'll be able to see general purpose robotics in my lifetime, but at least within manufacturing, you can see the solution applied in a few years. So that's why it's applied in manufacturing. But today I'm going to try and sort of talk about those three main topics. How can we sort of achieve these three: democratized programming, simpler, more intuitive robots, and robots that can adapt to us? So the first one is sort of training. The way we can democratize robotics is by training more and more people. Why training is important? So we know that the robotic industry is expected to grow significantly in the coming years. And obviously it's going to disrupt the global workplace. It's already doing so. There's already a global shortage of engineers, and these slides are a few years or a couple of years older now, so I'm assuming the numbers has grown quite a bit. But yeah, the gap is 85.2 million by 2030. What's worse is that 80% of the workforce of 2030, if not higher, is already employed. So the new graduates are not going to cover that sort of 85.2 million of shortage of engineers. Then on top of that, we've got new technologies like artificial intelligence, digital twins. They're complex sort of systems, and they sort of add to the complexity and put even more pressure to the skill base. We know that the skills that existed, that we need now, didn't exist 10 years ago, and as the technology progresses, these sort of keep changing. Even 5 years ago, 4 years ago, they didn't exist. Then we've got that 90% of sort of large employers and 2/3 of SMEs are facing skill shortages. So that there is an importance of sort of focus that the manufacturer need to a workforce that can adapt, with ability to adapt. There's also a war of talent, and we've got engineers that are becoming very expensive, which, as an engineer, I'm not complaining, but that's not sustainable, obviously. And then, yeah, the shortage is putting a lot of pressure on the sort of staff and reducing profitability. But most importantly, there's no sort of attention to the workforce that is aging. There's some surveys that we've conducted that show that only 15% of training is towards sort of workers, older workers. And as I mentioned before, we live in a world where tasks or sort of needs are constantly evolving. So we need the focus shouldn't just be on fresh graduates. But we tend to have people that have been at university 30 years ago, and that's the last training they've done, so they haven't really updated. So the risk to stay behind. So what can we do? So as the AMRC is part of the manufacturing, high-value manufacturing catapult, which is sort of a government-based sort of system of research RTOs that tend to sort of do exactly what we do, push research towards the higher TRL. And a couple of years ago, the high value manufacturing, they sort of released a manufacturing the future workshop. Is a workforce. It's a white paper that sort of explains how can we sort of improve and fix all these issues about training. I'm not gonna, because of time, I'm not gonna go too much into details, but the main sort of outcome is that we need to create sort of learning factories where there's a strong synergy between academia, industry, and governments, where they come together and they sort of create these sort of learning factories, starting from academia, by getting input from industry and also government, because there's an importance in regulations that need to be introduced quite early on in the learning journey. And then also learn from the best. One example is in Singapore, there's Skill Future, which is sort of a system where it's completely free, and anyone from any citizen of Singapore can sort of access them and then sort of learn. And is a government sort of funded scheme. Second point, so we need simpler, more intuitive robots. Why is that so much, especially in the industry? So every robot comes with its own proprietary language. Every brand, if you have KUKA, ABB, Fanuc, they work in a completely different way, and then you need to get trained in a specific sort of proprietary language. And also, the way you control these robots is with this type of pendants, which even looking at them, they're like a nightmare. It's completely hard, really unintuitive. And sort of the way when I look at this, those remind me of sort of computers in sort of early on computers that were sort of only they're only used by specific high-level sort of software engineers, and there were no sort of personal computers were not a thing. But then what happened? This man came along, and then he created the Windows ecosystem, and that sort of in a way helped to sort of create personal computers. Now everyone has got, without having necessarily an engineering degree or a software engineering degree, everyone's got their own computer and everyone can use that. And why is that? Is because computers become more intuitive. You don't need to be a programmer to sort of use your computer. You can just they're very intuitive. You can just sort of drag things around the environment, and then they can just interact with your computer. So what we need to do something similar for robots. This is a very sort of an example of what we do at the AMRC. And again, in terms of time, I'm going to be very quick. This is an example of, and again, this is a couple of years old. This is a system that we created of digital twins, where it's a virtual environment where any robot can just be, as long as it's ROS compatible, can be dragged into the environment and can be simulated. But also you can have sort of using augmented reality, you can have a hologram of the robot that sits on top of the real robot, and then you can drag the robot very simply. So you don't have to do any programming, and you can visualize the sort of virtual robot in front of you. And then if you're happy with the motion, you can just execute it as well. And then you can also give it some feedback. That feedback then is also translated with a speech interface that you probably won't be able to hear, but here I'm just sort of talking to the robot, and the robot sort of executes and then gives me some verbal feedback that is based on the sort of ROS messages that you get. And again, for terms of time, we're gonna just skip. Another sort of application for that one that we use, and this is more sort of industrial based, is we've created a project on perception-driven automated disassembly. And again, because we've only got 5 minutes and lots of questions, I'm going to try and skip through this. But the reason what we did around this one was sort of we need to sort of, there's a push for recycling and reusing of material. And when you get a product, the idea was, can we use robots to completely examine a new product and take it apart, and then put their parts, what can be recycled, what needs to go in sort of batteries need to go in a different container. Can the robot do all this disassembly and also sorting? Well, the answer was, we've done some research with Fraunhofer as well, and the answer is, well, no, robots will never be able to get a component they've never seen before and start disassembly on their own, because they lack that critical thinking. And also there's another topic that we can go into, that things are not designed to be disassembled, so they're not very pragmatic. So what we found around is the solution is to have humans still taking apart, using the sort of the critical thinking, taking apart the component once, removing it, and then creating a set of instructions that are very well defined, but still using human language. the same way that you would sort of create instructions for another human to do it. And then these instructions are translated into robot code. And then in that way, the robot is now able to completely and autonomously take apart that system, and any system that is identical to that one. So the human is only needed the first time to sort of have that critical thinking on how to disassemble the part. And this is sort of a sustainable way of using robot and human together, because you don't remove the human. You still need the human for the critical thinking. The robot does all the work for the human. Now, what we're looking at, and I don't have much to show at the moment, is can we use VLMs? And we started already doing this research. Can we use VLMs to sort of even further reduce the sort of the load on the human of writing down that specific table? Can by just using vision and communication, can the human communicate the exact same things to the robot the same way, but without having to create that table? And that's some research that we're doing at the moment. Unfortunately, I don't have anything to show as of yet, but maybe in a couple of months. And then this is a video, but we're going to skip it. So third and final point, we need to find a way to have robots that can adapt to us. And some research that we're doing in Wales, and this is not something I've done personally, but it's my colleagues in Wales, is looking at sort of ergonomic work envelope. How can we sort of develop an envelope where within the robot envelope itself that can sort of understand the best way for human and robot to work together? And what we're doing, and again, I can see the hands up, I'll just be very brief. The way that we can do is we need to digitize human state. And in order to sort of advance and understand also, the key point is there's a physical diversity. Not every human, because at the moment, what tends to happen, even if there's any ergonomics consideration, they tend to be universal for sort of a standard type of human. But obviously, we've got diversity with the humans. We've got men, we've got women, we've got people with different height, different weight, and different sort of length of arms. So what we try and do is we've created a set of experiment where humans and can interact with the robot. We collect all the data, and then we create sort of this working envelope to see what's the most ergonomic way to collaborate with the robot. And we've recreated the same thing in a virtual environment. So the same exact experiment can be recreated in a virtual environment. So you don't need to have the robot in front of you. And I'll just stop there because we've got no time left. And that's it. If you've got a question, let me know.
Thank you very much, Gianmarco. This was also, I think, really, really interesting, and I think really also very good perspective compared to the more research-focused perspectives we had in Jackie and Wenzhou. And I think we should take our time to have at least 5 more or 7 more minutes. We've got 2 more minutes on regular schedule, but I think we can take 5 more extra minutes to go through some questions. Well, maybe because I think we have some questions dedicated to single speakers, but maybe to have one general question combining a little bit all of your 3 talks. Maybe Wenzhou and Jackie, could you maybe say, because I think it was really interesting, the Valley of Death Gianmarco mentioned, and to see how they are tackling the different technology readiness level. From your point of view, Jackie and Wenzhou, where would you say the research you have presented, where do you see the technology readiness level currently of your research? Especially with the classification Gianmarco came up.
For my one, and I talk about 2 examples. One is the robot who work together with human workers doing blasting. And that robot was delivered to our industry partner for deployment. And if we want to say the TRL level, I probably could say TRL 7. The second robot for moving patients from bed to wheelchair, working together with nurses. That one, I would say probably TRL 6.
Yeah, for my side, I mean, I also know about some TRL level. Actually, most of my work actually not really close to the higher TRL level yet. But in this sense, actually, one of the limitation probably is that we have to investigate it further about what kind of users needs, like actually I have some experiences from the exoskeleton side. Developed the really nice exoskeleton in my opinion, but I just trying to exploit it to the shipbuilder workers in the rear field, the industrial field. Actually, I tested with them, and then they said that yeah, it was really nice experiences, and then everything is really good, and everything is functional. But the problem is they don't really want to use that thing to get a gain, because the problem is actually if they want to integrate such kind of thing in their process, actually have to make another process to take care of that things and then to manage it and then to guarantee the safer such kind of thing. So policy like way. So in that way, I was thinking maybe to having some like to successful human level collaboration. Actually, we also need to think about the user side, the user's aspect, something like that. So it could be, yeah, like that. Yeah.
Maybe I would take a couple of questions from the audience now, and I think there were two questions more dedicated to, well, the educational area and skill requirements. So I think there was one question for Gianmarco, where it was asked, what do you see as crucial skills for engineers, probably in the future, to design a human-robot interaction? And then later, I think earlier on, there was also, that was directed to Wanzhou, whether you have any specific courses for ergonomics and safety to recommend, but maybe Gianmarco, you could go first.
Yeah, I mean, that's when it comes to robotics, I think the skills required are the mare magnum. There's a plethora of different skills that you require, and I think the good news is I think it can come from different directions. And I think, for example, Jacinto is the right example. Yeah, he came from a completely different direction, from rather than starting from engineering, he came from psychology. So that's because again, in robotics is a combination, or you've got electrical engineering, control engineering, mechanical engineering, software engineering, that are sort of all combined together. And then when it comes to the human robot interaction, you need to start thinking about the psychology, you need to start thinking about sociology, the sort of importance of the safety as well, safety engineering. So the good news is that it can come from any of these directions, and robotics is a very friendly environment, so we welcome everyone. But then, yeah, in a way, you kind of need to know about all of them a bit roughly. I think what I've seen some people answering this type of questions is that the best type of engineering robotics is the one that's got what's called a T level of skills. So if you look at the graph where you've got all the different, you need to know a bit of everything of something in most things, and they need to be specialized in one specific sector. And I would say that's my answer. I guess it's not particularly helpful, but in a way, it's just, yeah, there's a lot. So there's lots of ways to enter in robotics and HRI or HRC.
Yeah, maybe Jacinto, you can.
I just want, thank you. Really shortly, thank you, Gianmarco, for mentioning my background. And I would like to say that probably it would be necessary to introduce some more engineering also in psychology degrees, probably, because we need to understand more what's possible or not. My experience over 18 years in human-computer interaction and 14 years over human-robot on human-robot interaction told me that probably this matching is important. And I would like to ask a question that is as an extra. If you want to reply later, even by email, I would be grateful. I would like to know what kind of issues you can find when you, in the past, collaborated with people that are focused maybe too much sometimes on human factors. Because sometimes the expert on ergonomics can be perceived like someone that is making the project deviate from the original core that should be engineering. Engineering is for humans in this case anyway, because we are centering the robots on the humans. sometimes there could be a mismatch, and this could be misperceived. I mean, the introduction of the human factors concept in engineering and especially in robotics.
I don't know what that question was. I mean, that doesn't happen to me necessarily because working with industry, we don't get enough people that work in ergonomics. So I think that's not a problem I've encountered, but I'm assuming that was for the others, maybe.
I'm already happy to know that you didn't meet enough people working in ergonomics. This is a really good sign.
Yeah, so personally would like to working with the ergonomic person, but yeah, the truth is that actually somehow the point of view is quite different. That's why I'm just maybe before we start with some working, we have to investigate it further as a user, but also like as a, with the talking with the discuss with the more ergonomic people, because and somehow our goal is the same, I think. Somehow they're trying to understand the human and then trying to make it better for their life, for the workers, through some more psychological way or the more physical way or the everything. But we need to, I think we have to discuss more about this thing to make the more better solution, to find a better solution. Okay.
Okay, I think we have really reached the end. Maybe just, and I'm sorry we couldn't come back to all of the questions, but maybe if there is still some interest, I think everyone is open to, I think the emails, the contacts are available. So, or you could just write an email to me and Jacinto, and then we could forward if there are still some questions open. Also, as I said in the beginning, the webinar has been recorded. So if you want to take another look again at some of the details, I think it will be soon on the IEA YouTube channel. And with that, I would really like to thank again, especially the speakers. It was really a pleasure having you. I think it was really, really interesting and insightful. Also, I would really like to thank you, Jacinto, because I think most guys are your contacts. So yeah, I think that was a really, really good picture. And I'm looking forward to our next webinars, and see you soon. Bye.
Thank you.
Thank you.
Bye.
Thank
Thank
you.
you.
Thank you, everyone.